All right, make sure you turn in page 103. Again, make sure you put it in the right slot in the metal tray at the front. Grab the notes. The notes you should be grabbing are the notes for 2.5. It should say section 2 or notes 2.5 at the top. It's 3D figures. And there should be 4 pages to it, so make sure you grab all 4 pages. And then you're just going to follow along, fill them in, and the assignments at the end there. We'll try to get through this as quickly as possible. So fill in what you need. If you need to stop the video or whatever, if I go too fast, just hit pause on the video. So 3D figures or solids. A polyhedron is a closed 3D figure made up of flat polygonal regions. So in other words, every face is a polygon, and we'll talk about what a face is here in a minute. But each one is some kind of polygon, so there's no circles, no curved parts. All the faces got to be polygons. Make sure you fill in what you need to fill in here, like the faces. A face is the section. I'm going to try to color one of these in. This whole thing here, this whole triangle, that's a face. This other triangle over here is a face, and all the other triangles are faces. The bottom's also a face, but it's a special face, and we're going to talk about here in a minute. It's the base, and we'll talk about it, but it is a face. That's a pentagon there. These parts are the edges, so each line segment where 2 faces come together is an edge. So that's an edge, that's an edge, that's an edge, that's an edge, that's an edge. That back here would be an edge. Remember that the dotted lines are the parts that if it was a solid figure you couldn't really see when you're looking at the 2-dimensional setup of it. Vertex. Each of the corners. So a corner is a vertex. This corner right here, this vertex, is a special vertex for this certain shape, and we'll talk about it here in a little while. But a vertex is just where 3 edges come to, or at least 3 edges come together to intersect. Might be more like on this one. There's more than 3 there. Here, this one here, there's 3 edges, 1, 2, 3 that all come together to intersect there. For this shape, which is a rectangular prism or a box, the one that we use a lot, vertex. So each corner, that's a vertex, that's a vertex. You connect 2 vertices, then that's an edge. And each of the sides of the box is a face. That's a face. That would be a face. So on and so on. And a rectangular prism like that one, all the faces are rectangles or squares. Remember, all squares are rectangles, so all the faces are rectangles. That's why it's called a rectangular prism. So just to go through it again, a polyhedron. All of these shapes, as long as they don't have any curve or circular parts in them, are polyhedrons. A face is just the side of the shape. An edge is just what it sounds like, one of the edges. The edge of, like the edge of this box, this edge, so on and so on. And then a vertex is where 3 edges come together. So there, those 3 edges all come together right there at that corner. A vertex is just a corner. Things that are polyhedrons. All prisms. There's all kinds of different prisms. We'll talk about them here in a minute. All prisms are polyhedrons. All pyramids are polyhedrons. Things that are not polyhedrons. A cylinder. A cylinder might look something like this. Not a polyhedron. A cone. A cone would look something like this. And a sphere. Or a ball. A sphere might look something like that. Those are not polyhedrons. So prisms, pyramids are. Cones, cylinders, and spheres are not. The base, or a base of a prism or a cylinder. The base, and draw in what you need to draw in. I think I forgot to. Maybe I never had it drew in. The bases. Oh, I know what I did. So this is a rectangular prism here. We're going to talk about how you name that here in a second. But a rectangular prism, a box. The base could be any two faces that match up. And the faces have to be parallel and congruent. So if we're looking at this rectangular prism the way it is, we might consider that face and this top face to be the bases. But if we took that rectangular prism and we stood it up on end, then we might consider this and that to be the bases. So in a rectangular prism, it really doesn't make any difference which two faces you consider the base or the bases, as long as they're two of the rectangles that are parallel to each other and congruent to each other. Or they're the two faces that are parallel to each other and congruent to each other. When you're looking for the base of a pyramid or a cone, then you look for the vertex that's like the point of the pyramid or the point of the cone. And the base is always the side that's directly below that, or directly across from it. I don't want to say below because it might be turned upside down or on its side or something. So if you had a cone that looked like this is your vertex of that cone, and then the circle part down here, or the circle part over here, is the base. So the base of a pyramid or a cone is always the one that's directly across from that one vertex. The parts in a prism or pyramid in the prism or pyramid, let's go with this pyramid first. This is our base. All the other faces are called lateral faces. So in a pyramid, the lateral faces are always triangles. The lateral faces in a pyramid are always all the triangles. In this case, this one has 4 triangles. So those 4 triangles are the lateral faces. In a prism, this shape is a triangular prism, and it's a triangular prism because when we look at it, remember the bases have to be the 2 congruent parallel faces. Well, the 2 congruent parallel faces are this triangle, so that's one base, and then this triangle, that's the other base. So those are the bases. All of the rest of the faces are the lateral faces. And this works for any prism. In a prism, all the lateral faces are rectangles. So in any prism, the lateral faces are rectangles. And remember, when I say rectangles, it could also be a square, because a square is a rectangle. So when I look at this one, this is a rectangular prism again, a box. If I pick this to be a base, and then that means this one up here is a base. All these four other rectangles or squares or whatever they are, those are the lateral faces. So a rectangular prism would have two bases, four lateral faces. A triangular prism would have two bases and three lateral faces. So you got to know, you got to be able to pick out which ones are your bases and which ones are just the lateral faces. When you're naming a polyhedron, you name it according to its base or bases. A triangular prism looks like this. It's got a triangle, it's got a triangle. Those are the bases. And all the other faces are rectangles, so it's named by its bases. That base is a triangle, so it's called a triangular, and all the other faces are prisms, so a triangular prism. And it's just like this one right here. That's a triangular prism. This is a base, that's a base. Notice that the other three faces are rectangles. This prism, we count the sides here, 1, 2, 3, 4, 5, 6. That's a hexagon. The other one down here would be a hexagon also. Those are the two bases. So it's a hexagonal. All the other faces are rectangles, so it's a hexagonal prism. If we wanted a pentagonal prism, got a pentagon, you got another pentagon. All the rest of the faces are rectangles. This is a base, that's a base, so that would be a pentagonal prism. So you find the base, that's the first part of the name, and then just add prism to it. If it's a pyramid, a square pyramid, that tells you that the base is a square. So like on this one right here, this is the base. It's a square. All the rest of the faces, in any pyramid, all the rest of the faces, all the lateral faces are going to be triangles. So if we had something maybe that looked like this, can't draw these very well, we might call that a rectangular pyramid. Pyramid. Because the base is a rectangle, and all the lateral faces, all the rest of the faces, there'll be four of them, are triangles. If we look down here, we have a pentagonal pyramid, because the base is a pentagon. So it's a pentagonal, and then all the rest of the faces are triangles. So every time you name something, you find the base, and name it according to that base. If it's a prism, then it's whatever the base is, and prism together. If it's a pyramid, it's whatever the base is, and pyramid. The one exception to that is something like a cube, but we could call that cube a rectangular prism. It's just in a cube, all these faces, no matter if it's a base or a lateral face, all 6 of the faces are all exactly the same. So here's just some different ones. These are in your notes there. You can look at them. Just pick them out. The ones that we didn't cover there, you got a cylinder. These might not be in your notes, but there's another slide that's in your notes. Cylinder, the two bases are circles, and then you got the other part of the cylinder, a sphere, like a ball. If we cut a sphere in half, then we have a hemisphere. So that's half a sphere. Notice that this looks like a cube. It could be a cube, but that calls it a rectangular prism. Means the same thing. This one, I don't like that. That's calling that a square prism. I'd rather never ever use that. Either use rectangular prism because all squares are rectangles, and you don't have to get confused by it. So this, I think, is in your notes. Different things, just different shapes. This is one that wasn't on there. A triangular pyramid. You really don't need the base part there. If we have a triangle, it could be a pyramid. It might look something like that. The base is a triangle, and all the lateral faces are triangles. It'd have 3 lateral faces. Then your cone looks something like that. Get rid of that. Hexagonal prism. Notice, got that base is a hexagon, the other base down there is a hexagon, then all the other faces are rectangles. Fill this in, right versus oblique. A right is just what we normally look at, that's the normal shape. Oblique just means instead of having all right angles in all the corners, instead of all these corners being right angles, it's sort of tilted or leaning, so that makes it oblique. We won't do a whole lot with oblique, but you do need to know the difference in the two. Platonic solids, named after Plato. Fill in what you need to fill in here. Platonic solids are regular polyhedrons. Regular polyhedrons, just like when we talked about regular polygons. Remember, regular polygons, all the angles were congruent and all the sides were congruent. Well, in a regular polyhedron, all the faces are congruent and all the edges are congruent. So in a regular polyhedron, and don't go by mine looks like some of these don't, like this one right here, doesn't look real great. That's supposed to be, those two are supposed to be a cube. Looks like it got stretched out when I put it on my PowerPoint. So all the faces are exactly the same. So if I'm looking at this octahedron, octa tells us that there's 8 of them. There's 8 faces, and they're all the same. Dodeca, we talked about that. That means there's 12 faces. A tetrahedron means that there's 4 faces. And if we look at those 4 faces, they're all triangles. All 4 of those triangles that make up that shape are exactly the same, or equal to each other. This one, an octahedron, there's 8 triangles. All 8 of them are exactly the same. This one, a dodecahedron, has 12 pentagons, and every one of those pentagons is exactly the same. On this last one, an icosahedron, sorry, I might not be pronouncing it correctly, has 20 triangles, and all those triangles are regular. So they're equilateral and equal angular. So it has 20 triangles that all look something like that, where all these sides are the same and all these angles are the same. Again, those are platonic solids. Platonic solids. Surface area. Fill in what you need to fill in on this part. Surface area is the sum of all the faces of a 3D figure, and it's always in square units because it's area. It's always in square units. So feet squared, centimeters squared, meters squared, so on and so on. Whenever you're finding the surface area, find the area of each face and then add them all together. So to find surface area, let's just do this. Find area of each face. Whatever the polygon is or the circle, we have all those formulas for find area of each face or each two-dimensional shape. Then add all areas together. There's formulas for some of them, and we'll talk about some of the formulas, and you will use some of the formulas, but most of them for like a rectangular prism, I'd rather you didn't try to use the formula. It's easier just to find the area of each face separately than add them all together, because when we start doing stuff, when we start modeling stuff for real life stuff, then it makes it more difficult, because a lot of times in real life it doesn't have all the faces. A net is a two-dimensional representation of a three-dimensional figure. So if I had a let's see, if I had a triangular prism, maybe something like this. This one's looking pretty ugly. If I had that triangular prism, the net would look something like this. We got 3 rectangles and 2 triangles, so the net might look something like a rectangle, 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 and then 2 triangles. All we've done is we took this three-dimensional shape and we've laid it out flat to make it two-dimensional. And when we find the surface area, this is sort of what we want to do, because then we want to find the area of this rectangle, area of this rectangle, area of this one. Find all 3 of those areas, and then also find the area of the 2 triangles, or the 2 bases, which we really only have to find the area of one of them, because we know that they're both the same. The bases have to be exactly the same. So we find the area of those 2, and then we add all of those areas together. So down here at the bottom, it tells you, use a net to find the surface area of all prisms, all pyramids, all right? For the other shapes, for spheres, cylinders, and cones, then we will use the formulas that you're going to get. But for prisms and pyramids, it's easiest to do this. So if I had a rectangular pyramid, boy, that's horrible, might look something like this. Well, I want to find the base, the area of the base, which is a rectangle. Then it's got a triangle here, triangle there, triangle here, triangle here. That's what the net would look like, and I'd find the area of all those triangles and that rectangle and add them all up. Look back at your other notes to make sure you remember the formulas for area of a triangle, area of a rectangle, area of circles, all the shapes that we've dealt with already. So again, a net, and I already did this on the other one. This is where I was going to draw the extra shapes. Let's just do a different one. If we were doing like a cone, the net of a cone, that's terrible. Ignore that. Net of a cone would look something like this, if that's our cone. And remember, that's going to have a radius across through there probably. Well, the net of that cone might look something like, and I can't draw these real well, might look something like that. Where this part is the part that curls around for the cone part of it, and then you have the circle. If you have a cylinder, net of a cylinder might look something like this. This part in here, if we laid it out flat, it would be a rectangle, and then it's got two circles, and the two circles are the same. So you find the area of one of the circles, and the other one would be the same thing, and this would actually just be a rectangle. Again, maybe a cube. I can draw a cube here. Might look something like this. The net of it would look, all rectangular prisms, a cube is a rectangular prism. All of them always have 6 faces. So it might look something like this. And if it's a cube, all 6 of those faces are exactly the same. If we're dealing with volume, surface area is, if I was making this cube out of cardboard, surface area is how much cardboard does it take to make the cube. Volume deals with how much can I put inside that cube. So the amount of space enclosed in that 3-dimensional figure. Volume is always in cubic units. So feet to the 3rd power, centimeters to the 3rd, meters to the 3rd power, instead of squared. Because again, what you're trying to find is, if I have this rectangular prism, I'm no longer finding the little squares that it takes to cover that certain shape. Now I'm finding how many of these cubes will fit inside that box, or how much water will fit inside that cylinder, or whatever it is. So it's always cubic units. Copy down these formulas. These are the formulas for surface area and volume of a cylinder and a sphere. So surface area of a cylinder, that means we're trying to figure out whatever this cylinder is. Maybe it's made out of metal, and we're trying to figure out how much metal it takes to make this whole cylinder. Remember, R stands for radius. You could also be given the diameter, which is just 2 times the radius. If we're doing surface area, and we want all of that, but maybe our cylinder, maybe it doesn't have a top, because a lot of times a cylinder like a bucket doesn't have a top, so we don't want that part. Well, if you look at this formula, this part of the formula, if we were to make a net out of this, again, the net of a cylinder would look something like this. 2 circles, the top and the bottom, and then this space going around it is a rectangle. This is the rectangular part. That's the area of the rectangle. This part is the area of the 2 circles. Well, if we don't want it to have 2 circles, the top is not there because it's open so we can fill it up, then we just get rid of one of the circles. And the way we do that is by just getting rid of that 2 right there. So if there is no top, the surface area is 2 times, the formula for surface area is 2 times pi times radius times height plus pi times radius squared. We just got rid of that 2 in the formula, if there is no top. Now for cylinder, or for volume, that doesn't matter. Because whether this has a top or not, it still holds the same amount of liquid or water or dirt or whatever you're putting inside that cylinder. A sphere or a ball, surface area is always 4 times pi times radius squared. That's for the surface area. That's how much, if you're making a kickball, how much plastic or rubber would it take to make that kickball, or a basketball? And then the volume is always 4 over 3 times pi times radius to the 3rd power. Be careful, make sure that you see that that's to the 3rd power, not to the 2nd power. So that means this formula is 4 over 3 times pi times radius times another radius. And remember, if they give you the diameter all the way across the circle, then you just need to divide that by 2 to get the radius. When you're plugging this formula into your calculator to do it, the way I do it is I put in 4, and this bar means divided by. So 4 divided by 3, hit equals, then hit times, then the pi button, then times whatever the radius is, then times whatever the radius is, times whatever the radius is, then hit equals, and it's going to give it to you. Don't try to use the ABC button, just put that in as 4 divided by 3. And then at the end, you're going to round off your answer to the nearest 10th or whatever the problem happens to tell you. For a cone, surface area formula is pi times radius squared. In the cone, that's the circle, that's the base of the cone. And then this part is the actual cone part, whatever you want to call it. And I'll talk a little more about some of this here in a second. Another formula for surface area is this formula. It looks a little more difficult, but it just depends on what you're given, and I'll talk more about that here in a second. If there is no bottom, a lot of cones that we deal with might not have that circular part of it, might just be the cone part of it, and so that you can fill it up or whatever, like a funnel or something. Well, then it doesn't have that circle. It doesn't have that bottom or top or whatever you want to call it. Well, all we do in this formula is we just get rid of the circle part. So the formula for surface area could be just pi times radius times s, and we'll talk about that s here in a second. Or it could just be pi times radius times the square root of radius squared plus h squared. Now on this, and different books teach different things, or have different letters. If I have this cone from the center to the edge here of the circle, that's the radius. From the vertex, remember that's that top corner, down to here at a right angle, that's the height. And then here's where you got to be careful. This, if I'm up here at this vertex and I'm sliding down the side of the cone, that's called the slant height. The slant height. Sometimes some different formulas and stuff, like this formula here, uses S as the slant height. So it uses the letter S as our variable. other formulas or other books or different things, and I think our book might use L, that cursive L, as the slant height. So it could be the L, it could be the S. It doesn't matter, you just got to remember that slant height is this right here. And one of the things that you're going to have to be able to do is know that, hey, if I have the slant height, I have the height and the radius here together, they form a right triangle. And then we're going to use that right triangle here in a minute, and we'll talk about that on the next couple of slides. That's all for surface area. So if you find the surface area, and you got to read the problem carefully and know if you have a bottom. Like again, a funnel wouldn't have a bottom. So if we were trying to find the surface area of a funnel, then we would just be using one of these two formulas. Volume, this is the formula for volume. Again, this H, the H is just the regular height, the height going straight down through here. So if I'm at the top of this cone and I'm dropping a rope down to the bottom so I can climb down it to get to the base of that cone, that's the height. Notice up here, this first formula, back on surface area real quick, this first formula uses radius and slant height, and this is why there's two different formulas. This formula uses radius and the regular height. You're always going to be given two of those three things. And if so that just makes it whichever formula you want to use. If you don't like this formula, then you could always use this one, and we can always find the slant height by doing something, and we're going to talk about that here in a minute. On this one, again, if I'm plugging this into my calculator to find the volume, how much will fit inside this cone, I do 1 divided by 3, hit equals, and then hit times pi times, so 1 divided by 3 times pi times the radius again, then times the regular height. Punch it into your calculator that way. A pyramid, surface area of a pyramid, what you're going to do is you're going to make it into a net. So if I'm looking at this pyramid that I have down here, that's my base, and then it's got 4 triangles. Sometimes all those triangles are the same, sometimes they're not. I'm just going to find the surface area, I'm going to find the area of all of those shapes and add them all up. Add up all the areas of all those. To find the volume, if we're looking for the volume, then it's going to be 1 divided by 3 times, this is big B, and we're going to talk about that here in a second, times the height. And again, the height, I'm up here at the top of this pyramid, and I drop a rope down to the base of the pyramid, that's the height. That's the height. The big B stands for the area of the base. If you already did the surface area, then you're going to know the area of this base, whatever it is. So you're going to take the area of that base, that's the big B, area of base of, and you got to not get all these different bases confused, because a triangle, remember in a triangle, this side would be the base in the triangle. Well, that's a different base than the base of the entire pyramid. So the base of the pyramid. So that big B is the area of the base. This base in the triangle would be a little b. Base of a for a pyramid is big B. That's that whole, the area of that whole rectangle or square, whatever shape that happens to be. So you find the area of it, Take 1 divided by 3 times that area times that height. Now again, in a pyramid, it has a regular height and it also has a slant height. So again, I'm dropping the rope down through here, that's the regular height. The slant height is if I was up here and I was on the side of this, or at the very top of this pyramid, and I was trying to slide down the side, that's the slant height. And again, slant height sometimes is given by an S, or maybe sometimes that cursive L, different letters, it doesn't matter, just know it's the slant height. This height also sometimes is called the altitude, which I have right there. To find that slant height, whether it's in a cone or a pyramid, I'm going to use a cone. If we have this cone, remember this is the radius, this is the height, this is the slant height. Well, we're just going to use that right triangle. And to use that right triangle, to find the missing side in that right triangle, we use Pythagorean theorem. The side across from the right angle, that's always the C, that's the hypotenuse. Hopefully you've learned that in the past at some point. We talked about it a little bit earlier this year. That's the hypotenuse. The A and the B are the two legs. One's here, one's here. Leg, leg. So if we're missing one of those, if we're missing one of these three things in this, then we can find the other. So let's say in this, if we knew the height of the cone was 4, the radius of the cone was 3, and we were looking for the slant height so that we could plug into the formulas, that's an S, then we would just plug into this formula. I already started 3 squared plus 4 squared. It doesn't matter which one of these two you put in. They're both legs, so it doesn't matter which order they go in. Equals C squared, and then you just do the math. 3 squared is 9, 4 squared is 16. That equals C squared. 9 plus 16 is 25. That equals C squared. And then to get C by itself, we take the square root. Use your calculator. You end up with C equals 5. So this slant height right here is 5 units long, whatever it would be. And then we could use that to plug into the formula to find the surface area or the volume or whatever we need to do. But you gotta know, make sure you fill in Pythagorean theorem. Make sure you know that C is the hypotenuse. It's always across from the right angle. So it's always, that hypotenuse is always over there. Find the height or slant height of each. We're going to do these together. These should be in your notes there. So in this case, I know the height. I know this base down here is 10. If I want to find the slant height, so the slant height would be coming down actually down the middle, one of the sides over here. It's sort of hard to draw 3-dimensional and 2-dimensional thing here. But it would look something like this. Got a right angle there. The height in here is 6 inches. The radius going from the middle out this direction, well, that's going to be half of this side. So if this side is 10, then that radius is going to be 5. And we got to be careful on this one, because if we look here, if we come down like the front or the back face down the side, it's sort of hard to see on this, but then our radius is going to be a little different because we're going to be going out that direction and up that way. Well, then we're going to have a triangle that looks like this, where that height is still 6, but going out from the center to the back side there is only 4 inches. So we're actually going to have 2 different slant heights. We're going to have one slant height coming down this side and this side, And then we'll have another slant height coming down the front and going down the back. So you gotta be careful. All you're gonna use those for is to find the area of your triangles, the area of each of these faces. So it's not gonna be that big a deal. But you might have to find two of them. Hopefully, on most of them, your base down here is a square, then they're all the same. So if we do that, then we use Pythagorean's theorem. We do 5 squared plus 6 squared, that's a 5, equals our C, which is over here across from the right angle. You can type all of this right into your calculator, then take the square root. So if I type in on my calculator 5 squared plus 6 squared, it equals, it gives me 61. Then I just take the square root of 61, and I end up with about 7.8. So this slant height is 7.8. And then I could do the same thing on this one. It would be 6 squared plus 4 squared equals C squared. That should have been C squared there. And then I just type this into my calculator. 6 squared plus 4 squared, it equals, and that gives me 52. And then I just take the square root of 52, second square root, and I end up with 7.2. So C equals about 7.2. So this side right here is 7.2. So if I'm coming down this way, my slant height is 7.2. If I'm coming down the front, no, hold on, I'm sorry, that's wrong, that's 7.8. Coming down that side, 7.8. If I'm coming down the front or the back, the slant height is 7.2. And then you could use that for whatever you need it for. If you need to find the area of this triangle, then that's going to be the height of the triangle. And then your base would be either 10, this over here, the base would be 8, and the 7.8 would be the height of the triangle. A little easier on the cone because the base of the cone has to be a circle. So this time we know the slant height. We're trying to find the regular height, so you got to be careful. So we have this, we're looking for that. We know this is 5, we know this is 12. You know where that stray mark going out through there? So this time your formula, instead of these two knowing both legs, now it's going to be 5 squared plus h squared equals 12 squared. And to solve that, we can do 5 squared, which is 25, plus h squared equals 12 squared is 144. Then we're just going to have to do a couple of steps instead of just one. So we'll subtract 25 on both sides. Those cancel out, and you're left with h squared equals, grab your calculator, 144 minus 25 equals 119. And then we'll just take the square root of both sides. And so on your calculator, you do square root of 119, and you get about 10.9. So this height in here for this cone is about 10.9. These examples are in the book. We're going to do them together just real quick. First thing on each one, I'm just going to answer this question down here at the bottom. The first one, is it a polyhedron? Well, we look at all the faces. If all the faces are polygons, then it's a polyhedron. So this one is yes, because all the faces are triangles. We look at this second one, ask if it's a polyhedron. This face is a circle. That's not a polygon, so that one's no. And then for this first one, we're just going to do all the bases, faces, edges, vertices, so on and so on. So the base for this, well, this certain polyhedron doesn't have a base. No bases. All right, so it doesn't have a base. just the way it's set up. It doesn't have two faces that are congruent to each other and parallel to each other. The faces, we're just going to name the faces. They're all triangles, and there should be 8 of them. So we're going to do triangle, and if we name this one, you're just using the 3 letters that make up that triangle. It doesn't matter which order they go in. QST. And triangle, we'll name this one over here QTU. Then triangle, we'll name the one in the back here QRU. And then triangle, this one back here QRS. And then we'll start on the bottom, SVT, triangle SVT. Then this one over here, triangle UVT. Then go to the back side back here. Oh, did I forget a letter? Oh no, I haven't. There it is. So it's this triangle back here, SRV. And then this one back here, RVU. And it doesn't matter which order you put the 3 letters in, but there should be 8 of them. 1, 2, 3, 4, 5, 6, 7, 8. The edges, remember that the edges are just each segment. So we're just going to use our segment symbol and name each segment. Hopefully I don't miss anything here. There should be 1, 2, 3, 4, there should be 12 edges. So QS, segment QS, segment QU, segment QR, segment SR, segment RU, segment UT, and segment TS. And then going to the bottom, segment VS. This is not for vertices, this is still for the edges. Segment VS, which is right here. Segment VU. Segment VT. Let's see, I missed something. What did I miss? Segment VR. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I still missed one. Let's see, I got VS, VU, VT, VR. I got QS, QU, QR. I forgot QT. Segment QT. So make sure you go in some kind of order and don't get confused like I just did and skip something. Then the vertices. Remember, the vertices are just the corners. So it's a little easier. So it's just all the corners. Well, we got Q, comma, R. Remember, these are all just points. U, S, T, V. There should, make sure I didn't miss any. 1, 2, 3. 1, 2, 3, 4, 5, 6. There's 6 corners on this shape. So we got all 6 of them. Bases, edges, vertices. And remember, bases are going to be 2 of the faces that are parallel and congruent to each other, but this one doesn't have those. So on this one, this is a triangular prism because the bases are triangles. So the first thing we want to name are those bases. One of the bases is triangle MLK. I'm going to try to write on this one a little less so I don't get confused. Triangle MLK. And then the other one's the one that's just like it on the other end, which is triangle HIJ. And again, it makes no difference which order you put those three letters in, but use your triangle symbol out in front. Then the other faces, we won't even put the bases in. The bases are faces, but we've already named them. So the other faces, there's three faces, and if it's a prism, then those faces are all rectangles. So we need 4 letters for each one of those. These, it does make a difference. You got to go around the shape in some kind of order. So you're just going around the shape in order. It doesn't matter where you start at though. So we're just going to say H, J, K, M. That's one of the faces, and there should be 3 of them. Then the bottom, if we start here, go I, J, K, L. I, J, K, L. And then the other one is this one, which is H, I, L, M. And there's no symbol for those. We just use the 4 letters and just make sure you separate them with commas. The edges should be 8 edges, and remember they're just segments. So those segments this time, make sure we use our symbols. Segment HI, segment HJ, segment IJ, segment ML, segment MK, segment KL, segment IL, and segment JK. There should be 8 of them. 1, 2, 3, 4, 5, 6, 7, 8. The vertices, those are just the corners. H, I, J, M, L, and K. There's 6 corners. 1, 2, 3, 4, 5, 6. Triangular prism. Again, if you need to stop the video at any time, if I go too fast, then just stop it. Next example in your notes there, identify the 3-dimensional figure that can model the beverage container, state whether the model is a polyhedron or not. So if we're looking at this thermos, the 3-dimensional figure that would probably best model that is a cylinder. Ignore that part going up through there. And then they ask us, is this a polyhedron? And we can say, not a polyhedron. It's not a polyhedron because it's got rounded parts. Remember, polyhedrons have to have just polygons. So it's not a polyhedron. Find the surface area and the volume of the rectangular prism. Round each measure to the nearest 10th. So we're going to use our calculators and round it off to the nearest 10th when we get to that point. First we'll do surface area, and usually I abbreviate surface area SA. To find surface area, all we're going to do is take this shape and sort of draw a net. Usually if I'm doing surface area, I don't draw an actual drawing of a net because I'm not a very good artist. I know that this is a rectangular prism, and I know it's got 6 faces, so I just do something like this. I draw 6 rectangles. And then if I look at those rectangles, let's say I take this end right here first. For a rectangle, I just need the length and the width, or the base and the height, whichever way you want to say it. Well, I can say that that's 6, and this is 5.2. I'm going to put it on top here instead of the bottom. Well, if that end has those 2 measurements, the other end in a rectangular prism has to be the exact same thing. So 5.2 and 6. Then let's say I do the top. Or let's do the bottom because it's a little easier. The numbers are on it. So that bottom right there, 5.2 is one of the sides, and then 10 On the other side, well, then the next one has to be 5.2 and 10. The top has to be that same thing. And then the faces I haven't done yet, this front face right here, or the back face. And sometimes you'll have to look at it and just figure out what each one is. So when I'm looking at this front face has one length of 10, and then it has this, which is the same as this, so 6. So 6 and 10, 6, 10. And to find the surface area, you just, for a rectangle, each one of them is a rectangle. Remember, it's just area equals base times height or length times width. So you just multiply. So you grab your calculator, and we do 6 times 5.2, and I get 31.2. So that's the area of that rectangle. Well, the area of this rectangle is exactly the same. Then 10 times 5.2, well, that's just 52. And those two got to be the same. 6 times 10, I can do in my head, that's 60. That's 60. And then to find the surface area, you're just going to add all those. So 31.2 plus 31.2 plus 52 plus 52 plus 60 plus 60. If you can do some of this in your head without writing it all down, that's great. Go right ahead. If not, then that's what you type into your calculator. 31.2 plus 31.2 plus 52 plus 52 plus 60 plus 60, and I end up with 286.4. Now what we just found is, if we were making this box out of cardboard, we figured out how much cardboard it's going to take to make all the faces. So that's units. Our units are going to be just the same as any area. So it's centimeters squared. For a rectangular prism, I forgot to put this in the notes, I think. That's why I was sort of struggling there for a minute. The volume of a rectangular prism is just length times width times height. So you just take the 3 measurements that you got and multiply them together. So it's just 6 times 5.2 times 10 this time. You might want to make sure you write that formula down somewhere in your notes there. So 6 times 5.2 times 10, we just plug that in our calculator. 6 times 5.2 times 10, and we get 312. And our units for volume, remember, it's how many little cubes will fit inside this. So it's how many little cubes it takes to fill up that box. It's always got to be cubic units. Surface area and volume. Find the surface area and the volume of the cone. So if you look back at your notes, we had formulas for both of these. So you just look back and you find the formula for a cone. I'm going to do this. So with a cone, first, if we're going to do the surface area, there was 2 different formulas. If you look back at your notes, one of them dealt with slant height and one of them dealt with the regular height. You can use either one, I don't care, and I'll set up both of them here in a minute. But if we're going to use the shorter one, which uses slant height, then we have to find this slant height. And the way we find that is by using this right triangle. So it's going to be 8 squared plus 15 squared has to equal our slant height here squared. So I'm going to, it's still C in Pythagorean theorem, so I'm going to use C squared. And you can grab your calculator and just type all of this in. 8 squared plus 15 squared, it equals, and then you got to take the square root of that number. That come out to be 289. So we're going to take the square root of that to get C by itself. Well, the square root of 289 is 17. So that means this slant height over here is 17 inches. So if you want to use that formula, you can. I'm going to set up both of them, and then we'll just do both of them. One of the formulas then would be its slant height equals pi times radius squared. Well, the radius is 15, plus pi times radius times slant height. The other formula is pi times radius squared plus pi times radius times, and then it's got that square root where it's r squared, which is 15 squared, plus the height. This here is the height. Remember, that's the height. This is the slant height. Plus, sorry, that's the regular height. That's 8 squared. You plug either one of those two into your calculator. This one, you might have to plug it in separately and do like this part, then times that by this, by the 15, then times it by pi, then hit equals, then put these two in, and then add the two answers together. However you do it in your calculator, it doesn't matter. If you found the slant height, you could punch all of this into your calculator just like it is right there. So if I grab my calculator and I hit pi times 15 squared plus pi, and some of you may have to hit second on your calculator to get to the pi, times 15 times 17, and hit equals, and we end up with 1507.96. Well, when we round this, we round to the nearest 10. That's going to make that 9 a 0. And we're actually going to round this number up 1. So our surface area is going to end up being 1508.0. And since that's surface area, it's area, so it's inches squared. Volume, the formula for volume is 1/3 times pi times radius squared times the height. Well, we know all those numbers, so it's 1/3 times pi times the radius is 15 squared times the height, this height, which is 8. And when I plug it into my calculator, I just plug it in as 1 divided by 3, hit equals, then times pi times 15 squared times 8. And I end up with the volume, and this one I'm going to have to do the same thing. It ends up 1,884.95. That tells me to round all that up, so it's 1,885.0, and our units are inches, and it's cubed since it's volume. If you did this formula up here for surface area, you should have gotten real close to the same answer that we got right there. So in this next example, it says a New Year's Eve, each year millions of people watched the descent of New Year's Eve ball in New York City. The New Year's Eve ball is a geodesic sphere that is 12 feet in diameter. So just looking at that real quick, if it tells us it's 12 feet in diameter, that means the radius of it is 6 feet. It weighs 11,875 pounds, is lit by 32,256 LED lights, and is covered with 2,688 crystal triangles. How many lights are contained on the ball's surface? And that should give us a big hint what we're dealing with. Within an area of 4 square feet. So what we're looking at here is we're looking at the surface area, and this is the surface area of a sphere. So if you go back in your notes and find the formula for surface area of a sphere, the formula is 4 times pi times radius squared. Well, we know what radius is. We found it. They told us the diameter, and we just cut that in half to get the radius. So the surface area of the whole sphere, the whole ball, is 4 times pi times 6 squared. And I'm just going to plug all that into my calculator. So 4 times pi times 6 times 6. And I get about 452.4. And that's going to be in feet squared because it's surface area. Well, they didn't ask us for that answer. They asked us how many lights are there in a 4 square foot area. So what we have to do there is we have to set up sort of a proportion is probably the easiest way. We know, they told us, that the whole ball contains 32,256 lights, and we know that that is in a surface area of 452.4 square feet. So you got the lights on top, and you got feet squared on bottom. Well, we want to know how many lights, which we don't know, so we'll make it X, are in 4 square feet. And to solve this, all you do, solve a proportion, you cross multiply. So when I cross multiply this way, I get 452.4 times X. And when I cross multiply the other way, I grab my calculator, 32,256 times 4, and I get 129,024. To solve that, I just divide both sides by 452.4. These two over here cancel out. Remember, X just stands for how many lights are in that part that we want to deal with. You already got this big number here on your calculator, hopefully, unless you get clear. So you just divide that by 452.4, and I get 285. It said how many lights are contained. It's about 285.2. So for lights, we'll just say it's about 285 or 286 lights. Second part here, this time it says that Tony's repairing a section of the ball that is 8 cubic feet. Well, it's cubic feet, so now we're not dealing with surface area anymore. Now we're dealing with volume. And the formula for volume of a sphere is 4 divided by 3 times pi times radius cubed. So we're going to find the volume of the ball, and then we'll have to probably set up a proportion like we did on the other part. So this is just 4 divided by 3 times pi times, and the radius was 6, so it's going to be 6 times 6 times 6. I'm going to write it out that way so I don't forget, because that way I don't have to try to cube it on my calculator. So when I punch this in my calculator, I do 4 divided by 3, then I hit equals usually. Then I hit, just to make sure that my calculator is not telling me the wrong thing, then times the pi button, then times 6, times another 6, and times another 6, and hit equals, and I get about 904.8. So the volume of the ball is about 904.8 cubic feet, or feet to the third power. Now, we don't want the whole thing. We only want 8 cubic feet. So we know the weight of the whole ball is, let's see what it tells us, 11,875 pounds. And that has a volume, that whole ball has a volume of 904.8. Well, we want the weight of just 8 cubic feet. This is cubic feet down here. So again, all we're going to do is cross multiply. We cross multiply this way, we get 904.8 times x equals, we cross multiply this way, solving a proportion, that's 11,875 times 8, and I get 95,000. Then you're just going to divide by 904.8, and that's going to tell us how much that part of the ball that he's fixing weighs. So I already got the 95,000 in my calculator, so I just hit divided by 904.8, and I get 104.9, it's about 105. And that's going to be in pounds, about 105 pounds. And it's in pounds because that's what we were looking for up here. If this top one here was in pounds, then that X that we were looking for has to be in pounds. That's your assignment.